So principal component analysis is based on linear algebra, on eigenvectors and eigenvalues of matrices. You don't necessarily have to understand those details in order to use principal component analysis. If you have a package that will perform principal component analysis, then it will just convert the data from a high dimensional form into a low dimensional form that you can display. So as we lay out data and look at ways of laying out data based on relationships, it's useful to look at some other techniques for laying out data, even if the data does have variables or attributes or coordinates associated with it. So one of these techniques is called principal component analysis. If I have a data set like this one, each data value has an x coordinate and a y coordinate, but you can really see that the main variance of the data is happening along this diagonal direction, and the data isn't varying much perpendicularly to that direction. So the x coordinate doesn't entirely capture the data, and the y coordinate doesn't entirely capture the variance of the data. The variance is actually happening in a different direction. So we can look at the variance of a data as being the actual dimension where things are changing along the data, and it may not be exactly the x direction or the y direction. It may be a combination of them. And as we look at higher dimensional data, we may find that the data is varying in some direction that's a combination of x, y, z, w, however many dimensions you have. And so principal component analysis helps us find these directions where the data is varying a lot, and also the directions that the data is varying a little bit, and then we can reorient it so that we can just display the dimensions where the data is varying a lot and ignore the directions that the data is varying a little bit, and then align those dimensions with the displayed dimensions. So in order to perform principal component analysis, we have to analyze the data. First, we have to take the data, and then we have to subtract the mean. So for each of these data items, we're going to add them up, divide by the total, and that'll give us by the total number. And then that'll give us the mean. We subtract that from all the data. That centers the data about the origin. And then we're going to compute this covariance matrix. It's a big matrix. If our data elements are 4 dimensions, x, y, z, and w, then the covariance matrix would be a 4 by 4 matrix. It'll have this many dimensions by this many dimensions. And it's just the data items after you've subtracted their mean multiplied by the other coordinates of the data items and then averaged. And that covariance matrix will yield a symmetric matrix because, for example, yi times xi is going to be equal to xi times yi. And so you can think of a matrix as something that a large matrix as something that transforms a sphere in high dimensions into some kind of ellipsoid. It's going to stretch it out in a certain direction. And when you square that matrix, multiply it times its transpose, it's going to create a square symmetric matrix similar to that covariance matrix. When we pull out the eigenvectors and the eigenvalues of that matrix, these are directions that when you multiply the matrix times that direction, it's the same thing as just multiplying it by a scalar value. So these are directions where if a matrix is stretching a sphere into an ellipsoid, they're the directions of the principal axes of that ellipsoid. And so if you have a lot of variance, you'll pull out an eigenvector in this direction that's stretching the sphere out into a long ellipsoid. And there may be 2 principal directions, in which case that sphere gets stretched out into this cookie shape. And so principal component analysis finds those eigenvectors, the direction where the data is varying the most, and then it ignores the small eigenvectors, the directions where the data is varying the least, and that way we can display the 2 or 3 most varying directions of data without displaying all of the dimensions of the data. So here's an example. I worked with a group of people a few years ago on a method for computing the geometry of a scaffolding to support bone growth in damaged mandibles. And so we needed some geometry for a mandible in order to figure out a healthy mandible and a damaged mandible to be able to do a subtraction operation to find this damaged piece. So if we don't have an undamaged mandible, how can we find a mandible that was the shape of the damaged mandible before the damage happened? And the way we did this was we scanned in a bunch of these mandibles, and we specifically measured the shape of these 5 data points. And so we had this big database of 40-some mandibles, and each data point, each of those 40 data points was 15-dimensional, because each of these 3 data points was 3-dimensional. So 5 3-dimensional data points gave me 15 dimensions. So I could describe the shape of a mandible as a 15-dimensional point. We then performed principal component analysis to find 3 main variations, three of the directions in this 15-dimensional space where these mandibles were changing the most. And they were kind of this direction here that pulls the jaw down, this direction that causes the jaw to kind of extrude in the front, and then a direction that caused the jaw to move to the side. And so based on that, we could plot all of our data points, and this is an example of the mandible, all the different data sets of our mandibles plotted as a single, just overlaid on top of each other. Each one of these corresponds to a position in this space of mandibles. And the 3 dimensions here that I'm visualizing these mandibles in corresponds to a direction of variation that I found from that principal component analysis, each of those 3 dimensions. So each one of these points corresponds to a point in a 15-dimensional space, but I'm plotting them in the 3-dimensional space according to the direction of their highest variance as represented by the eigenvector of that covariance matrix. And so that performs a form of dimensionality reduction where we can take high dimensional data and plot it in a low dimensional space for visualization by basically focusing on the dimensions where we're seeing variation and ignoring the directions where we're not seeing variation in the data. So in order to implement multidimensional scaling, you need to do an optimization. You don't necessarily have to code up your own optimization to do that. For example, when I computed the multidimensional scaling of the cities in my example, they were computed in Excel using an optimization package I enabled. So you don't have to write an optimization algorithm from scratch. You can just use an existing optimization program.